Our next topic is greedy algorithms. So the greedy strategy of solving algorithmic problems is another classic and very important strategy that is used. So we have seen the brute force of these backtrack search that explore all the possible solutions and some optimizations to that, then the branch and bound, the pruning strategy. And greedy, uh, the greedy strategy or the greedy algorithms, it turns out to be a very specific and in many cases very optimal way of um, solving algorithmic problems. Um, but as we had mentioned in one of the previous lectures, greedy algorithms are the most specific or the least general kind of strategy. The strategy of greedy, of solving problems using the greedy strategy is the least specific strategy. That means it applies to the least number of cases. Okay, so in general, in your world of algorithmic problems, there are all kinds. There's a universe of algorithmic problems. And if your problem can be solved using a greedy strategy, you have to consider yourself to be really, 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 really lucky. Okay, because when they usually work, they're really great and they're really fast and yeah. So that's a bit discouraging. So that's to say that would mean that most of the times greedy algorithms wouldn't work, but still there are a lot of very beautiful algorithms, should say oftentimes they're very intuitive algorithms that can be solved using greedy strategy. So it's worth studying this strategy. Okay, and there are other reasons why we study greedy algorithms. Oftentimes, I've noticed in students, whenever an algorithmic problem is given to solve, then naturally the solution that oftentimes we come up with is a greedy strategy. Okay, so it's very intuitive in many ways. We feel naturally, we are often tend to come up with solutions that are greedy in this nature. Okay, that doesn't mean they're correct, and most of the times they are actually incorrect. But it's a natural way of thinking, right? And many times the obvious way of trying to solve a problem might be a greedy strategy. Okay, and there are other reasons. Many times, if a problem is known to be hard, we can still kind of compromise the optimality of the solution by applying some greedy strategy. We'll see of that later in the course. And also, yeah, so many heuristics can be solved using greedy algorithms. Okay, so what are greedy algorithms exactly? So there is no formal definition for an algorithm to be greedy, but as we know, we have seen that when we talk about these combinatorial search or optimization problems, we think of our solution, our solution that we are looking for. We said it is a discrete object, right? The solution we have said is a discrete object. So, for example, we had the array for the n queens problem, which had these n parts, and we thought of a solution as one possible configuration of this, one possible way of filling up this array, which did not conflict. Okay, so so what greedy algorithms does is it constructs this solution piece by piece, right? So first it'll maybe try to fill up this slot, And after it does that, then it will try and fill up this slot, and then it will try and fill up this slot, and so on. Okay, so we are constructing solutions piece by piece. And the main question that we try to answer is, how do we pick the next piece? Okay. So for example, in this case, we try and figure out, maybe we have filled up this value and we are trying to figure out how do we fill up the next slot? How do we pick that next piece? Okay, so this might sound to you that it's the same as backtrack search. What's the difference? Okay, so one crucial thing about greedy algorithms is that once we pick a part of the solution, that is forever going to be part of our solution. Okay, that is guaranteed to be part of the optimal solution. Okay, that's the crucial difference. Okay, so if you remember in backtrack search, we might pick a value for this slot and then maybe pick another value and then realize that, oh, this is a conflicting position, and we might backtrack. Or we might have picked certain values up till this point, and then when we look at the next value here, we realize that we cannot place it in any way such that it does not conflict with one of the previous values that we have assigned. Okay, so in that case, we backtrack. We discard some option that we had considered and change the value and proceed with the search. Okay, so what happens now in greedy is, in these greedy algorithms, somehow this part, how do we pick the next piece, is answered in such a way that the way we pick the next piece, we are guaranteed that we do not have to backtrack. Okay. We are guaranteed that the piece we picked will be part of the optimal solution. Okay. So this is really the key point. And right, so the way it ends up is that there's no backtracking that is done. Okay. So I like to think of this analogy of, we said, of this recursion tree, right? We had talked about in the previous lecture how you can think of any combinatorial search or optimization problem as having to explore this entire recursion tree, and the leaves of this recursion tree, we said, these are complete solutions, right? And somewhere amongst these complete solutions is an optimal solution, or maybe one or more optimal solutions to a problem, right? And this tree can be really, really huge, and exploring it can take a lot of time, right? So, so in the regular backtrack search, we would maybe go down this path and here realize that maybe this does not satisfy the constraints, and backtrack, and then explore this, and then backtrack, and so on, right? Until we explore the entire tree. Now, the analogy I feel often in greedy algorithms, what happens is we maybe start from this point and we look at, simultaneously, we look at maybe all the possible options. Okay, and we just somehow are able to pick one of the options. Okay, so we pick one of this branch, saying that this is the branch I want to go down. Okay, and then we somehow say this is the choice that I want to make here, and we go down this path. Okay, So we've picked the first part, and then again we have a bunch of choices, and we are somehow able to figure out that maybe this is the choice I want to make. This is the way I want to pick the next value. Okay, I want to pick the next piece, and I go down this patch. Okay, and so on. Okay, at each step we do some calculation, some kind of analysis, and sometimes it may be very quick. And we pick the next value for the next slot. Okay, we pick the next piece. And the great thing about the way greedy algorithms works is that we do this at each step, and when we finally reach the leaf, right? When we finally reach a complete solution, okay, we go down maybe all this and we reach the complete solution, what we are guaranteed that this solution is going to be an optimal solution. Okay, so somehow the way these algorithms work is we don't have to explore this entire recursion tree. Just by doing some calculations at each step, or maybe some pre-processing at the start, we are able to quickly decide which branch we have to go down, and we are guaranteed that when we complete the exploration, not exploration I should say, when we complete this traversal, when we reach a leaf, we are guaranteed that we hit an optimal solution. Okay, so this gives some intuition, I guess for me, it gives some intuition of the power of these greedy algorithms, that I do not have to explore any of all these other branches, right? So you can imagine the savings and runtimes. Okay, and indeed greedy algorithms tend to be really fast. Okay, so that's the reason why we study these algorithms. Okay. One thing about greedy algorithms, well, is that oftentimes the so-called obvious strategies, okay, and oftentimes when you give a problem, you're convinced. Many times students say, no, so this is it. This is, we do this, this is, you pick this and pick this, and this is, that will give us the optimal solution. Okay, you're convinced in many ways. It seems like the obvious way. And these obvious strategies, most of the time, I should say mostly, do not work. Okay, doesn't mean that we should not think about them at all. If something is obvious, we do not consider it at all. That's not the point, but you have to be very cautious, right? When something seems obviously correct, it most likely may not be the case. It may be wrong. Okay, and what that implies in turn is that a proof of correctness is crucial. Right? So without a proof of correctness, your greedy algorithm may be worthless. Right? If you want to find the optimal solution and you don't have a proof of correctness, your algorithm may not be worth much. Right? So this is really the key part in greedy strategies, is how do we prove our algorithm to be correct. Okay, oftentimes the algorithm itself may be quite straightforward, as we'll see in examples, but actually understanding why it is correct, why it indeed returns the optimal solution, will take effort. Okay, and that is where we'll have to sweat it out, right? So many times this process of how to pick the next piece, right? This might be tricky. It may not be obvious at all. Sometimes if you have a solution in front of you, if you have an algorithm in front of you, you may not recognize it as, it may not seem to be the correct algorithm. Okay, so we'll see that for an example right away, that an algorithm, an obvious algorithm may be incorrect. Something that we feel that should work may be incorrect. And showing that it is incorrect also might take some work. Okay, we'll have to find a counter example, and sometimes it's not obvious. But crucially, when we have an algorithm that we think is correct, we have to give proof of correctness. Okay, I've seen algorithm courses where instructors have explicitly stated in their examination papers that for any problem that they're asking to solve, if the students give a greedy solution, okay, by default they fetch 0 marks. Okay, so that means that just the solution without any proof of correctness may not be worth a lot. Okay, so it might be quite easy to come up with these solutions, but how do we actually show that they are correct? Okay, so this is going to be a big component that we'll be discussing in greedy algorithms. Right. So another thing I want to say is that we have already encountered greedy algorithms in the past, right? So maybe you're aware, some of you have probably realized that, for example, the minimum spanning tree problem that we solved using, say, Kruskal's algorithm. Okay, so Kruskal's algorithm is a very classic example of a greedy algorithm, right? At a discrete object that we have to pick is that tree, right? So a set of basically a set of edges, right? Because it has to be connected. We have to have all the vertices in the graph, but we have to pick some set of edges such that it forms a tree, which is spanning and which has the least cost, right? So that is a discrete object. And what Kruskal's algorithm does at each step, it picks the lightest weight edge, right? It tries to pick a lightest weight, the next lightest weight edge, and if no cycle is formed, it will say that I can guarantee that this edge is going to be part of some MST, right? It's going to be part of some optimal solution, and we recurse, right? So oftentimes, if we can figure out this step, right, how do we pick the next piece? If we can somehow figure that out, many times in greedy algorithms, then you can just recurse. Okay, you can just apply that step recursively, and one by one, you will end up picking the right pieces. Okay, but figuring out how do we actually pick that one piece is really the crux, right? So for example, in Kruskal's, we pick the next weight, the next edge with the lightest weight, and check that it does not form a cycle, right? If we do that, then we just loop over, right? We do this iteratively for each edge in the graph, right? And we are magically guaranteed to find the overall optimal spanning tree. Okay, so Dijkstra's algorithm is another example of a greedy algorithm, right? And so is Prim's algorithm, right? So these are all examples of greedy algorithm that we already encountered. We'll see more in these week's lectures. And yeah, so this is the theory to keep in mind, okay, what we have just discussed, all these things. Just something that you should revisit after we have maybe seen the examples. Maybe a good thing would be after we have discussed all the examples to come back to this particular video and see if it makes a little more sense. Okay.